Sandra Cerrai from Maryland. Asymptotic results for a class of stochastic RDE with fast transfer theorem and so it's acting on the boundary.
Thank you very much for the invitation, for the opportunity to spend such an interesting and nice period here at the Newton Institute. In this talk, I would like to present a result which I have obtained in collaboration with Mark Friedlin, and which is appearing, soon in Unanswered Probability. I start with the equation just to fix the setting in which I'm working. So, I have to. Okay, I have the microphone. I'm not sure. Is it working? Okay, so I speak louder. So here I'm considering this reaction diffusion equation. You see, this is the equation which is perturbed by this stochastic term, and the stochastic perturbation is given with this multiplicative term. And I have this equation is an equation in a bounded domain D of Rd, and the boundary condition is inhomogeneous, you see, is given by this term with the conormal. But on the other side, I have this other stochastic term. So here in this equation, in this system which I am considering, I have the noise acting inside of the equation, but I have also a noisy perturbation, a noisy term which acts on the boundary. And here I give also the initial condition. So I write here the equation just in such a way that we have always the equation. So du epsilon dt is 1 over epsilon a of u epsilon plus f of tx u epsilon plus and I have and then the initial conditions. Okay, and as I was telling you, D is a bounded domain in Rd with D greater or equal than 1. Okay, and here you see that in this equation there is a parameter. There is this small parameter epsilon, which is in front of the diffusion term here, and is also here in front of the conormal derivative. Okay. As you can imagine, we are interested in the asymptotic behavior of the solution u epsilon as this small parameter epsilon goes to 0. Just to fix the idea, what we have is the following. D, the domain, is a nice bounded domain in Rd, which has a regular bounded, so that I can use all the regularity result for second order uniformly elliptic operators. So I am in a very good situation. And A is a uniformly elliptic second order operator, and this term is the conormal derivative. So it's the natural normal derivative associated to this diffusion operator. The coefficients f, g, and sigma, which appear in the equation, are measurable and satisfy reasonable conditions. So sigma is uniformly bounded, f and g are Lipschitz continuous with respect to the right variables. So I have very nice condition also on the coefficients. And concerning the noisy perturbation, which are here in the equation, you see I have a noisy perturbation here, and I have a noisy term here on the boundary. And what I assume is that WQ and WB are cylindrical Wiener processes, which are defined respectively on L2 of the whole domain for WQ for this term, and on L2 of the boundary for this other term. And in dimension d equal 1, we can just take here the white noise in space and time, and here I do not have any condition because I have an interval, so I have just 2 points, and I put 2 Brownian motions on the endpoints of the interval, okay? But in dimension d equal 1, we can deal also with white noise in space and time. This class of equation, typically describe the evolution of concentration on some chemical components, and in this situation you have to take into account that the concentration is not constant in time, and so you have dependence on time, so you have a partial differential equation, and also you have some randomness which arise in the rates of reaction, and so you have this stochastic term. And what typically happens in this system is that you have different scales for different terms in the equation. So the rates can have different orders, or also you can have different orders for the rates and for the diffusion term, for the transport term. And this is exactly the situation which we are considering here. Here we are considering the evolution of the concentration of these chemical components in a situation in which the diffusion term, the transport term, this term, is much bigger than the reaction term, okay? And so this is a quite natural situation, and one wants to see what happens when this parameter is very big. So how it's possible to approximate the solution, the concentration. And what we have and what we will prove is that in this case, a sort of averaging result happens. So the solution of these SPDEs can be replaced by the solution of a suitable one-dimensional stochastic differential equation. And of course here the great advantage of this result is that you can replace a quite complicated object as a stochastic partial differential equation by means of an object which is which is much more simple to handle, which is a stochastic differential equation in one dimension, okay? So this approximation result is useful to simplify this very complicated object. And we do not only prove that U epsilon converges to the solution of a suitable stochastic differential equation, but we also study fluctuations of the solution around this average motion. And so we prove a sort of central limit theorem in this situation. So this is the averaging result. This is what happens. What we have to assume here we have this operator A, which is a second order differential operator. We have the diffusion, which is associated to this second order differential operator. And what we assume is that this diffusion admits a unique invariant measure with exponential convergence to equilibrium. So under the assumption that there exists a unique invariant measure with exponential convergence to equilibrium, the result which we prove, the first result which we prove is the following one. We prove that if we take the difference of U epsilon and V, and we measure this difference with respect to the L2 norm, with respect to the invariant measure, we take the supremum on a finite interval, and of course here we have to take this interval, this delta has to be far from 0, because at 0 we do not have convergence, because at 0 is natural, U epsilon is a U naught, but V, the limit, has to be the integral of V of U naught with respect to the invariant measure. So you do not have convergence up to time t equals 0, but if you are a bit far from 0, you have this uniformity in time, then you take expectation, you take the limit, and you get that this limit is equal to 0. So we get this sort of limiting result for U epsilon. And here V is the solution of this object. I will describe in a simpler way what is this object, but just to have an idea, dV solves this equation, and here you see we have these new coefficients f hat, g hat, and sigma hat, and these coefficients are obtained in, it's easy to predict what is the definition for f hat, g hat, and sigma hat. They are just the average. They are obtained by taking the average of the coefficient with respect to the invariant measure. So what is important here is that this, and you see also for the initial point V naught, you have the average of the initial point u0 with respect to the invariant measure. And what you have here is that you have an equation which do not depend on x, on the space variable. So you are starting from an equation in which you had space and time, and now you have an evolution. In the limit, you have an evolution which depends only on time. So the x variable disappears because you just average with respect to the invariant measure. But this is a quite obscure expression for the equation. So just to fix the idea, just to have an idea of what sort of equation we...
Just a question, probably missed. What is the boundary condition you associate to A?
What? The uniform this condition.
But the Neumann, homogeneous Neumann boundary condition.
Yes.
Okay.
Yes. I mean, here I am on the concrete equation. Then I will give you all details, and then I will tell you which boundary condition. Of course, when you introduce the semigroup, you introduce the semigroup associated to the homogeneous Neumann boundary condition. But here you have this extra term. Okay.
Why isn't the invariant measure just Lebesgue measure?
What?
Why isn't the invariant measure just Lebesgue measure?
I didn't write the invariant.
No, you wrote it as mu.
This is mu. So in general, you have an invariant measure,
But
okay? But in the, for example, in the self-adjoint case, then this invariant measure is just the Lebesgue measure divided by the measure of the domain D. So in general, you can have an invariant measure mu, but the example which you have in mind when you have self-adjoint diffusion is just
I thought your A was in divergence form.
No, it's not in divergence form. It's given. I wrote in divergence form. Probably I was not. Because it's divergence form in the sense that you have d over dxi, aij, d with respect to dxj. So the main term is in divergence form plus bi dxi. I'm sorry, but just to tell you that I write the first part in this way, and so to this first part I associated the conormal boundary condition, the conormal boundary. So d over d nu for me is just of a function phi is a nu gradient phi, okay? And this A is this matrix. So in this sense, this is why I said in divergence form. Yes, when you don't have this term, then you have just the Lebesgue measure, and then you just take the integral with respect to the invariant, to the Lebesgue measure.
Mu is the normal.
Nu is the normal at the boundary. So this is a matrix which acts on the normal, and it
A-N. Normal, not conormal.
this is the normal. Yes, you're right. You don't. Yes, nu. If nu is a yes. Yeah. But this is the normal, the real number.
On the other form, it's d over d nu.
Yeah.
So that was
This is the normal. Okay, and so now I wanted to give a description, a more understandable description of the limiting process. So what you have is that the law of the limiting process coincides with the law of the solution of this reasonable one-dimensional stochastic differential equation, and here I can give an explicit description of the coefficients of the limiting equation. So here Wt is a standard one-dimensional Brownian motion, and these two coefficients are given explicitly. So let's start from the drift phi. The drift is just given, as one expects, as the integral of f tx v for v, and v now is a real number, it's just a real number. I take the integral of this object with respect to the invariant measure, okay? And for the diffusion term here, the diffusion coefficient in front of the noise, I will give in all details later on when I will state the theorem, but just to fix an idea in a simpler situation, otherwise it's a mess. If you are in the self-adjoint case, so you do not have BI, you have just this term, so the invariant measure coincides with the Lebesgue measure multiplied by this normalizing constant, then what is possible to prove is that this diffusion coefficient psi has this expression. So you just take this function g, you multiply by, you take q of g, q is the covariance operator in front of this noisy part. B is the covariance operator in front of, which appears in this noisy term, and I have the sum of these two terms. So I would like to stress also this fact that here the randomness in the equation was coming from these two terms, this term which was in the equation and this term which was on the boundary, but on the limit you just get a standard one-dimensional stochastic equation in which you can put together the two terms on the boundary and in the equation together. Okay, so in some sense the noisy term on the boundary disappears and is put together with the other noisy term. Okay, so this is the term. And for example, in the case the dimension d is equal 1, so you have a white noise in space and time, then the diffusion coefficient is just given by this simple expression. Okay? So, as I was telling you, we do not prove just the convergence of u epsilon to the average motion, but we also study the fluctuations of the average of u epsilon around the average motion. So we studied this normalized difference, and we were interested in the weak limit of this normalized difference as epsilon goes to 0. And what we could prove is that in the case, instead of having a multiplicative noise, okay, here the noise depends on the state, on u epsilon. If you assume that g do not depend on u epsilon, so you are in an additive noise case, in this situation, it is possible to prove that this z epsilon t converges to some Gaussian random field, I naught t, which depends on t and x, and we have weak convergence in this L2 space with respect to the invariant measure. And this process, this Gaussian random field, I0tx, so now this object depends also on the space variable, how it's natural to be. This is explicitly given. I will give you later on the complete expression, but again, to fix an idea and to have an idea of what sort of object we have, in the case we do not have any noise acting on the boundary. Okay? In the case we have homogeneous boundary conditions, so we have only this noisy term, the limiting Gaussian random field which we obtain from the fluctuation is given by this object. So this is nothing else than this is the sum over k, the interval from 0 to plus infinity of eta, and yes, here we have this. So assume, for example, that Q is lambda k, so assume that you are in a, this is the condition which we will have. So here you have g of t dot ek, and you compute this at x, and you subtract the integral of gt y ek y with respect to the mu y. Okay, and you take the beta kt. Okay, and of course one has to give a meaning to this infinite sum, and you see here I have an infinite sum and I have an integral which goes from 0 to plus infinity, and one has to give a meaning to this object, and one has to prove that everything is convergent and converges to a reasonable object. Okay, the convergence of this integral from 0 to plus infinity, I think is easy to believe because you have a spectral gap for the invariant measure, for the convergence of the semigroup to the invariant measure, and so it's reasonable that this integral from 0 to plus infinity is finite. And with the good conditions on these eigenvalues, and by using the invariance of the invariance of the measure mu and a heat kernel representation of this semigroup, by putting together many ingredients, it's possible to prove that this object is well defined in L2 with respect to the invariant measure. And this is actually the weak limit of the normalized difference. As I was telling you, the result is not just when here we have homogeneous boundary condition, but is in the general case. And of course, you have to add another term, which is a bit more complicated, but I will describe this term very soon. I would like to stress the fact that when here there is a mistake, because here is S,
And then the bracket interchange with the exponential.
huh?
Left bracket interchange with the exponential.
They interchange because
Interchange.
yes, they
If you start correcting, then first bracket put behind exponential. The first bracket. Put
no, because this is an invariant measure. This is an invariant measure, and so I can, no, it's correct. Oh,
But it contradicts your formula.
no, because what I'm saying is that you can take pi here, but you can also take pi here, and this is exactly the same, because this is an invariant measure. Yeah. You can interchange. So what you have in general is that, I mean, since this is an invariant measure, and this is what you can interchange due to the invariance. Okay. And as I was telling you, if here this term G do not depend on time, the limiting Gaussian process do not depend on times, does not depend on time. So it does depend only on the space variable. So now I have to fix some notations and some. So here, as I was telling you, this is a nice bounded domain, and this is the operator. So you have this term in divergence form, and then you have this first order term, and I assume the natural uniform ellipticity condition, and I have smoothness for the coefficient. So everything is okay for the second order operator. And here, just to fix notation, H is the L2 space on the domain, and Z is the L2 space on the boundary of the domain. So here, just to answer to your question, I denote by A the realization in H of the operator A loaded with the homogeneous boundary condition, okay? And as it's well known, this operator A generates an analytic C0 semigroup, so we are in a very good condition, and all the theory which we have for stochastic integration, everything can be applied. So the main hypothesis, which I said in words, but now here is written, what we have is that the semigroup ETA associated to this diffusion operator A admits a unique invariant measure mu, and also we have this exponential convergence to equilibrium. So what we have is that if we take the difference of the semigroup minus the mean of the function h with respect to the invariant measure, this can be estimated in this way. We have H is L2 on the domain with respect to the Lebesgue measure, but then there is also H mu, which is L2 with respect to the invariant measure. And with this notation, I mean, this is the way I denoted this mean. What is possible to prove is that H is continuously embedded in H mu due to the invariance of the measure and due to the heat kernel representation for the semigroup. And also, I mean, it's possible to prove that this measure can be represented in this way for some smooth function greater or equal to 0, but I do not really need this representation. So what I need is that H continuously embed in H mu. As I was telling you before, if you have that this is equal 0, so clearly the operator A is self-adjoint, and what you have is that the first eigenvalue, the first eigenfunction corresponding to the 0 eigenvalue is just the constant, and then mu as this representation, and gamma is just this alpha 1. So for the coefficients f, g, and sigma, I assume the following conditions, which are quite natural conditions. So what I assume is that they are measurable and they are Lipschitz continuous with respect to the third variable, uniformly with respect to the other ones. And for the coefficient which appears here in the inhomogeneous boundary condition, this sigma, I assume that is measurable and is bounded. Okay? is uniformly bounded in X in any bounded interval in time.
Sorry, what's the boundary condition for your A? Is it also Neumann boundary or?
Zero.
0, the homogeneous.
Zero boundary.
Yes, yes, yes. A is the operator with this equals 0. So it's the homogeneous. And this is a
Neumann boundary.
Neumann boundary, yes, yes, yes. But here you have this homogeneous term. And so here, just to fix notation, because I will need, in order to write my limiting objects in a reasonable way, I introduce this capital F, this capital G, and this capital sigma in this way. So these are just the composition and multiplication operator associated to this reaction, this term, these local terms, okay? So what do we assume for the noisy term? I assume that WQ and WB are both cylindrical processes which are defined in L2 of the domain and in L2 of the boundary. And they have covariance operator Q and B. And of course, I have to assume some condition on this covariance operator in order to have solutions in the reasonable functional space. And so I assume this structure for the two cylindrical Wiener processes, and here EK and FK are orthonormal bases in the two Hilbert spaces where I work, L2 of the domain and L2 of the boundary, and I have this expression. And here beta k and beta hat k are sequences of independent standard Brownian motions. They are all independent and they are all defined on the same stochastic basis. And of course, I have to assume conditions on the on these weights which I put in the noise. And so, if the dimension, the condition is only in dimension d greater or equal than 2, because in that case I have to color the noise. And so I have this condition on the weights which I put here in front of this noise, and I have this condition for the weights which I put in the, for the component of the covariance here on the noisy term. And what I would like to stress is that in both these two situations, I do not assume that they are Hilbert-Schmidt. So I cannot use Ito formula and all this stuff, and I have to work in a more complicated way. And this condition gives me white noise in space and time when I am in dimension d equal 1. So I cannot use Ito formula, so no Hilbert-Schmidt conditions. And these are quite natural conditions, and these are the same conditions, at least for this one, which you assume when you want to prove that you have solutions for this class of problems. So this is nothing extra than what is usually assumed, okay? So here you do not need to assume any extra condition in order to have your limiting result, just to have solutions for the stochastic partial differential equation. And of course, here I need something different because I have this noise on the boundary. So here I have 20 minutes. So here I have to describe the boundary stochastic convolution for those of you who have never seen these things. But here I start from this deterministic situation and I introduce the Neumann map as in this way. So I consider this elliptic equation in a domain D. I impose these boundary conditions. So I have this inhomogeneous boundary condition, and for any h, I denote by n delta h the solution of this elliptic problem, which exists for some delta, for all delta sufficiently large. Okay, so depending on my condition, I have some delta 0, and for all delta greater or equal than 0, for any h, I have a solution n delta h. And this operator n delta, which take a function which is defined on the boundary to a function which is defined on the whole domain D, is called the Neumann map associated to my second order operator. And what you have is that the Neumann map has some sort of regularizing effect, in the sense that it transforms a function which is a h alpha on the domain to a function which is h alpha plus 3/2 on the whole domain. So it has this regularizing effect, which is much better than the regularizing effect of the corresponding Dirichlet map. So the case of Dirichlet boundary condition is much more complicated. Here, the Neumann map, what is good in the Neumann map is that it has this very nice regularizing effect. Okay? So in view of this, I have to give a meaning to this object, so in the stochastic case. So from the elliptic problem, I pass to the parabolic problem. So now I consider this parabolic equation in this way. Here I have the operator A, here I have the conormal boundary condition, which is inhomogeneous. And what is possible to prove is that here the solution can be represented by this expression. So with this expression, you can represent the solution Y of this parabolic problem. And you can prove this directly when V is sufficiently large, but then you see that you can extend this, this formula is still valid for V, which is less regular. And so it's natural to say, okay, I have this in the deterministic case, why not to use this representation of the solution in the stochastic case? And so, in view of this formula, one tries to give a meaning to the solution in the stochastic case. So now we have this situation, okay? Here I have my parameter 1 over epsilon, and I have this problem. So I'm not considering this term and this term, so I'm taking f and g0, and I'm considering this equation, and I try to give a meaning to a solution for this problem. And what I say, in analogy to what I have in the deterministic case, I say if I use the formula above with A replaced by A over epsilon and delta 0 over epsilon and so on, and instead of the deterministic term you take this stochastic term, so you just replace pieces, okay? And what you can say is that the solution of this problem when f and g are equal 0, I say that this object, which is here on the right-hand side, is I say that this is a mild solution for my problem. Okay, so I say that I can write the solution of the stochastic problem when I have this noisy term on the boundary in this form. Okay, and here you see that I have the stochastic term, I have the Neumann map, I have this object. And of course I have to give a meaning to this object, and I have to see that this is well defined in the right space. But this is something which is known in the literature, so this is nothing new. The problem is that I am concerned now with the limiting behavior of this object with respect to epsilon. So I have to study what happens for this object when epsilon goes to 0. So now I have the theorem which says to me that if I fix an initial datum u0 in the space H and for any t, p, and epsilon, what I have is that there exists a unique mild solution for my problem. And of course, in the definition, I have all these terms. These terms comes from the reaction term, these terms comes from the stochastic convolution corresponding to this stochastic term, and then I have this extra term which comes from the boundary term. So I have just these three terms, and I have to prove that there exists a solution, and also I'm interested in a priori bounds for the solution. But here the situation, once you give a meaning to this object, the meaning to this object is well known, no problem, and in order to prove existence and uniqueness is not really a problem. So what you have is that for any epsilon you have to prove that this is well defined, and this is more or less known, but the problem is that you need to have uniform bounds for this object. Then you have that this mapping for the stochastic convolution, which comes from here, where you have multiplicative noise, is Lipschitz continuous, and also you have uniform bounds for this object. And then due to the Lipschitz continuity of coefficients, you do not have any problem to prove existence, uniqueness, and a priori bounds for the solution. So once you have this, you want to prove the averaging result. And so you take f hat as this integral, so you take the reaction coefficient here, and you average with respect to the invariant measure. And what you have, due to the good conditions on f, due to the fact that h embeds continuously in h mu, so you have all very good conditions, so you have Lipschitz continuity of this object and all good conditions. And also it is possible to prove, and this is the key, the first key estimate, you can prove that if you take this difference, you see here in both places I have u epsilon. If you estimate this difference, this is the typical term which you have to estimate all the times you are proving an averaging result. You take this with u epsilon, this with u epsilon, and you have to prove that this goes to 0. And you have a very nice estimate for this, which is, and this estimate of course comes from the a priori bounds for u epsilon and from the fact that you have this exponential convergence to equilibrium, so you have this. once you have this, now you have to introduce the average diffusion coefficient, and the diffusion coefficient is given in this way. So G hat THZ is just the product of G times Z, and then you integrate with respect to the invariant measure. And again, this object G hat is well defined, is Lipschitz continuous, and it has all nice property which you need in order to give a meaning to the equation. And the second key result, the second key point in order to prove the averaging result is that if you take the stochastic convolution for any epsilon fixed and you take the difference with this object, now you see you have averaged everything here, because you see this G hat acts on the noise, and so you have also to average the noise with respect to the invariant measure. Okay? If you go to the definition here, G hat of THZ is, you take the product of G times Z, and here Z is the noise, and you have to integrate everything with respect to X, with respect to the invariant measure. Okay? So here I have everything integrated, so I do not have anymore the X variable, and you take this difference, and this can be estimated in this way. And so now I introduce this new object, which is just this integral, this stochastic integral, where X has disappeared. Okay? And now I have to introduce the average boundary coefficient. The average boundary coefficient is defined in this way. You take sigma times h. This is a function defined on the boundary. You take this to a function defined on the whole domain by means of the Neumann map. You integrate with respect to the invariant measure, you multiply by this delta naught. And this is the coefficient which comes from this term in the limiting equation. And this is again well defined due to the good regularizing property of the Neumann map, and everything is well defined, and so this defines a very nice bounded linear operator on Z. And also again here we can prove this estimate in this case with this epsilon to some power lambda p, which is well defined. And again I have this W hat, which is defined in this way. And so now I have this one-dimensional stochastic differential equation, and which is this one, and this can be written in this form. Okay, nothing. And so what you have is this theorem. For any U naught and for any p greater or equal than 1/2, for any t positive and for any delta, you have this result. Okay. And here the proof now the proof is finished, because you just take the difference is this plus this, but this term is exactly the collection of the terms which I have studied before, and these are exactly the terms which are going to 0, and so it's trivial now to prove that I have this convergence. Okay. So now, in the in 12 minutes which are remaining, I would like to speak about the normal deviations. So in the case of normal deviation, I have to assume some more restrictive condition on the coefficients. So for example, it's natural to assume that f is differentiable, and I am assuming that the derivative is also Lipschitz continuous. So I have bounded derivative. I have, yes, Lipschitz continuous derivative. And I assume that here I do not have any more dependence on U epsilon in the diffusion coefficient here. So I am dealing with additive noise. Okay? And also I have to assume some regularity in time for G and for sigma. And I have to assume that both sigma and G are order continuous with any exponent, but they have to be order continuous with respect to time. So under these three conditions, okay, and then I have all this term, I have this theorem. And the theorem says that if I take Z epsilon, I'll call you, Z epsilon is U epsilon minus V divided the square root of epsilon, what I have is that this Z epsilon is weakly convergent in H mu, so in L2 with respect to the invariant measure, to this Gaussian random field. And you see here in this Gaussian random field, you do not have anymore the term F. Term F has disappeared. So the only terms which you have are the terms which comes from the boundary, okay? From the noisy perturbation. You do not have any more. So for example, if G and sigma are equal 0, you have just convergence of this normalized difference to 0. The F disappear. This is something which was surprising in some sense, but you do not have anymore the term with df, which usually you get when you have these sort of limits. And so you see that here the limit just involves the two noisy terms. And it's given by this expression, which is a bit complicated, but okay, I will explain. So, for example, in the case G and sigma are equal 1, okay? So you have completely additive noise, no coefficient here, and no coefficient here. This I naught Tx, which you see now, I wrote ITX, but actually does not depend on t. Here you do not have anymore the dependence on time, is given just by this sum. So this expression becomes much more simple. And here the only point is that you have to give a meaning to this object. But for example, look at this object. This is very well, I mean, this is well defined, it's clear, because this is, if you take the expectation of the square of this object, this is just the sum of lambda k squared divided by alpha k, and my assumption are just that this sum is finite. Okay, so this is completely well defined, and here I have this term which comes from this. And notice that here delta naught disappear, you don't have anymore, you don't see anymore this delta naught. So this delta naught is just a constant which I put, which I choose, but actually there is not in the real formula, okay? It does not depend on delta naught, and is given by these two terms. Oh yes, sorry. This is plus infinity, yes. These two terms are two integrals from 0 to plus infinity, as is written here. Okay, thank you.
I'm sorry, is it for t greater than delta naught? Or
Hmm?
Is it for t greater than delta naught?
There's no t.
What is
For
t?
any t greater than the 0?
This is for any t greater than 0, yes. Yeah. I don't what?
T greater than delta or some delta to avoid this t equals 0.
You should be
Pointwise, so you don't need delta here.
It's pointwise, but
But it should not be one. It says for any t bigger than 0.
Yeah. This is the part. I mean, here the presence of this t in some sense is not so. This is the t which comes from here. Okay. The presence of the t. So if you don't like to have t, you just take g, which do not depend on t, and then you do not have any more t in the formula, in the limiting process. Okay?
So can I ask a question? So it's
Yeah.
a general theorem that the second integral doesn't depend on delta 0, right?
Yes, this is the fact that this integral, you choose this delta naught because this is the delta naught which allows you to solve the Dirichlet problem, I mean the elliptic equation with the inhomogeneous boundary condition. So you start from this delta naught, and for delta naught you have a solution. But you see that here, this does not depend on delta naught, and the reason, I'm not sure that if this is true, it should be true for in any situation, but the reason is that you see here you have delta naught of this object, and at a certain point when you write this solution, the solution of this term, what you get is that you have n delta naught star of ek. Okay, you have to compute this. And this is, it's possible to prove that this is, in the case A, Ek is minus alpha k Ek. I don't know if you see this. What you prove is that this is 1 delta naught plus alpha k, Ek restricted to the boundary of T. Okay, and so here you have this term delta naught plus alpha k. And this term disappears with this term. Okay? And so this is the reason why at the end you don't see any more delta naught.
But you had to choose delta naught in terms of epsilon, or was it?
No. Delta naught do not depend. Delta naught do not depend on epsilon. Delta naught is that delta naught which allows to solve the problem delta naught minus a v equals 0, and then you have the solution V is denoted by n delta naught h. And for some delta naught, you have a solution for this problem. Okay?
So can't you take the limit delta naught goes to 0 and define that to be the value of that second integral?
What do you mean?
It would be nice not to have delta 0 appearing in your
Ah.
formula.
Sandra, take delta 0 to be equal to 1.
Yeah.
And stop all this
Okay. I mean, because what I'm saying is that, yeah. Because in some sense, this delta naught compensate with this, the delta naught here compensate with this one. Okay. And so, yes, thank you. 1. I take 1. So if I take 1, you don't see delta naught, but yeah. Because what I'm saying here, I was trying to explain you, is that this cancel with delta naught minus A. And so, yes, probably it's not a very nice expression, but if, okay, you take 1, or what you have, 1. So this is the limit. I have 5 minutes. And so you see, from the limit you have these two horrible terms, which are not so horrible if you write them in reasonable situations. So these are objects which you can handle. And so you have this IG and I sigma, which are given by these two expressions. And of course, there you have infinite sums and you have all these nasty things. But still, it's possible. It's not immediate, but it's possible to prove that you have this convergence of these integrals. So these are objects which are well defined in L2 omega with values in L2 with respect to the invariant measure. So these are nice objects. And so for the proof of the central limit theorem, one proceeds as usual, okay? So you take z epsilon, and z epsilon can be decomposed in the sum of these three terms. You have these objects, you have this and this. This is the natural object which you always have. Then you have this and this. This I epsilon is given by these two terms, and these are the two terms which at the limit give you the interesting term. And R epsilon, since I use R, this is a reminder, and so this is something which goes to 0. And is given by the sum of these three objects. So the first step in the proof, so now so the epsilon is given by this, and these are the three terms. So first of all, one proves that for R epsilon, that R epsilon is a reminder, and so this goes to 0 as epsilon goes to 0. And this is the only term which you have, apart from, this is what you have in the deterministic case. So in the deterministic case, everything collapses to 0, okay? So you do not have any term involving f, okay? And so you have this limiting when epsilon goes to 0. Now, since I got rid of this term R epsilon, I introduce a new object, which is a z, Greek z, epsilon, which is given by this without R epsilon. And so the point is that since I have that this goes to 0, I have that z epsilon minus Greek z epsilon goes to 0. And so now I have just to study the limiting behavior of this Greek z, okay? And the lemma, the crucial lemma, the fundamental lemma is to prove that this z epsilon is weakly convergent to these Gaussian random fields I naught. This is the point. And in order to prove this, I have to represent this z epsilon in some way. So I can represent z epsilon as this integral plus I epsilon. I epsilon is the term which at the limit give me the two terms which I described earlier. And this HTS is given by this expression, and K epsilon S is given by this expression. So you can write this, and this is an elementary computation. What probably is a bit less elementary is the proof that this object can be estimated in this way. So if I take the expectation of the square of this object, this is less or equal Ct epsilon to some power gamma, which is positive. Okay? So this term goes to 0. Okay? And so now we have to prove that I epsilon is weakly convergent to this object. Now this is what is remaining. And in order to prove this with a change of time, what you have is that the law of I epsilon is equal to the law of this object. This object is given in this way. And for this object, I have this. And so the proof is finished.
Thank you.
Is there any particular reason why you don't allow the sigma to be
Because I do not see even how to give a meaning to the Neumann problem in that case. What do you mean? Because if you have, because here you should have sigma Tx u epsilon at the points at the boundary. And so you need to have some
Well, if
trace for the solution. I mean, for me it was not even clear how to deal with the Neumann problem, with the inhomogeneous Neumann problem, when you have here the inhomogeneous term which depends on u. I looked through the literature and I didn't see, probably there is some results, but I couldn't find anything reasonable in order to handle the Neumann problem in homogeneous, because here is the problem that you have to take the trace of the function which you put here on the boundary. You need some regularity for that. You need H1.
You can take Neumann.
condition
Huh?
of Q.
Yeah. No, okay. Probably it's possible, but our reason was not to have problems with the deterministic part, with the analytic part of the argument. That was the only reason.
Be very natural to have also a fast reaction to.
Yes, another possibility, for example, is to have this reaction term split in two parts. Yes, split in two parts. So one part which is fast, another part which is not fast. That would be also natural and interesting. I don't know. But we thought about it. I mean, we said, okay, it would be, I don't know.
Other questions?